There's a few things I want to say before starting off. First off, my name is Chris. I'm a PhD student here at Sydney. I haven't done too much tutoring with courses, so you may not see me around. But I sort of study things which aren't that related to this, but I think this is a really cool sort of look at some maths which is quite different to what you may traditionally learn in undergrad. But because we've got a nice small audience, I also want to emphasize that I feel like every single person in the audience should be able to follow everything up until a point. And that point may come halfway through, 3/4 through, last 5 minutes, but if you're feeling lost in the first 5 minutes, please ask a question, right? If there's an easy thing that could clarify, I really want you to ask, because I'm not assuming you've seen anything before, and I'm going to be a little bit vague. So because in this sort of maths, it's much easier and much better to get the vague, intuitive picture of what's going on, and then give precise definitions. If you start with precise definitions, they can be awful. So just in that way, I sort of want to check if people have seen some things before. So could you please put up your hand if you have seen or heard of a group before? Alright, seen or heard of a group? Okay, okay, fantastic. So I want to describe the problem, which is really a puzzle. That is another reason why I really want you to sort of ask questions. This is a puzzle that you can sort of go away with. You can ask people, right? Puzzles in maths are often better than theorems and stuff, because you can tell a puzzle to some random person, they can think about it, and and it's interesting. So we can really think of this talk as just 45 minutes of attempting to understand this puzzle and to understand it well, because it leads to some very interesting maths. So the puzzle is as follows. I'm going to draw a picture. Say we've got a painting. This is my favorite painting, and we want to hang it on a wall with 2 nails. Alright? Here is a boring way of doing this. And you can see that if we put the string around these 2 nails here, the painting would not fall. Okay? This isn't too tricky. And you can see that if we removed one of the nails, the painting would still not fall. Okay, so nothing revolutionary is going on. And so the problem of the puzzle, find a way to hang a painting on 2 nails such that if you remove either of the nails, the painting falls. Okay? Such that if either nail is removed, the painting falls in. And I'll briefly say, this is the sort of puzzle that you might find in a magazine that has puzzles. The sort of more mathsy version of this puzzle, so maybe I'll say puzzle plus plus, is exactly the same thing with n nails, such that it falls if any is removed. Okay, so we can see, this is just a special case of this, but if you're just messing around drawing pictures or playing with string, you're not going to be able to solve this for all n simultaneously. That is a much more involved problem that requires, theory and really understanding what's going on. Okay, now, does anybody have any questions about the statement?
I have a question. If you remove one of the nails, wouldn't the painting still be on the other nail? Why would it fall if you remove one?
Exactly. So this is not, right? This is an arrangement of hanging up a painting such that it does not satisfy this. So let's do another one. Say a nail there. What if we go just around one of them? Well, yep, the painting, it hangs up. But if you remove this nail, it still hangs up. So this is also not a valid solution. And let's, even more complicated thing to show what we're allowed to do, say we could go, and connect up like that. I mean, and now it's not obvious, right, whether if you remove a nail it'll fall. And I'm pretty sure I did it in such a way that this still doesn't work. But at least this should tell you that you can, do some interesting things in this problem. Not all of your answers are going to be as simplistic as this. Now, does anybody sort of want clarification about what precisely we're modeling here? Because this is a nice problem in that, we have our physical intuition, but it's not necessarily in a mathematical way. And formulating this mathematically is a difficult problem which I'll mostly be avoiding. But because of that, I just want everyone to sort of be aware of, or to understand the statement of the puzzle. Does anybody have any questions? Or if it came a bit later, I can repeat it. So, this is the most important thing I want to understand. Is that a question? No? Okay, so this is the puzzle. How can we do this? Oh, and I will say, I've seen riddles in the past where the solution is like completely outside the scope of what you think you're allowed to do, and those are sort of annoying. So, like, the solution is of this nature. It's not some exotic thing. I don't know, you take a sledgehammer to the wall or something. Like, yeah, you really can just do it. It is, and it does make sense within the confines of the problem. Okay, and so if you're bored, you can sort of try and think of a solution before I get there, because I'll be getting there a bit slow. Okay. So now, let's approach this sort of mathematically. We're starting with 2 nails. Maybe we can look at 2 and think, okay, 2 is too difficult. Let's go to 1. Okay? How can we hang up a painting on 1 nail such that it doesn't fall, and if we remove the nail, it falls? Okay? Well, let's do an example. Oh look, there's an example. It's hanging up, you remove the nail, it falls. And in fact, it doesn't take too long to think, no matter how you wrap it around, once you remove that nail, the painting is going to fall. Right? So really what the challenge is can we work out a way of telling when the painting won't fall? Right? So we could wrap it around like this, and then do this. But now this isn't hanging up. Okay? How can you see that? Well, imagine the where is this hanging? Maybe that's a good question. Even in the one-dimensional case, it's not always obvious. But let me draw one which definitely isn't. Oh yeah, and see, I'm not necessarily caring about where this connects to the painting. I mean, you can really think of it as like, I don't know, a point mass or something. It's just a little bit more visual when it's, imagine this is a very contrived problem that someone might want to actually do in their house. And we can see here, right, like, this isn't gonna hang up. When you remove the nail, it falls, but it doesn't satisfy the first part of the problem, which is actually hanging up. Okay, so now we're going to analyze this one nail case in sort of, like, how can we tell ahead of time? Right? Like, if I drew a hell of a lot of spirals, how do you tell whether it'll fall? So the idea that we're going to use, and already proving that this strategy in fact works, requires the tools which I'm not going to introduce. But it's going to be intuitive, so put on your intuitive hat, abandon all rigor, that's fine. So what we're going to do is consider the path that the string takes, and we're going to look at how many times it goes clockwise around the nail, and how many times it goes anti-clockwise around the nail. Okay, so for instance, if it goes there, it goes clockwise, and then it goes anti-clockwise, and then it goes clockwise, and then it goes anti-clockwise. And this won't hold it up. Okay, so let me say that a bit better. You imagine from the perspective of the nail, you follow this string, and you keep track of how many full revolutions you do around the nail when you get back to your start. Okay? And so then the theorem is that so this is the one nail, that the painting falls if and only if there is an equal number of clockwise and anti-clockwise times you go around the nail. Okay? And we can sort of see that this is more or less what happened. We go once clockwise, once anti-clockwise, once clockwise, once anti-clockwise, and get back to where we start. So the idea is if you wind around it a bunch of times, then it's going to hold up. And if you don't wind around it, so you wind and then you go back, then it won't hold. Okay? So painting falls if and only if the string has equal number of clockwise and anti-clockwise. Let's say clockwise and anti-clockwise rotations. Clockwise slash anti. Now, I shouldn't even call this a theorem, because I'm really not defining it, but I'm going to use this sort of as a stepping stone for understanding the n equals 2 case. Right? So, like, what is the original problem? We start with something, and we want to remove a nail, and then we want it to fall. So, if we start, and then we remove the nail, we will be in the one nail case. So that tells us that we will need to have this work if we want it to fall. Right? So even this sort of trivial analysis of, like maybe an easier way to understand this theorem, and in terms of my quite poor phrasing, is that if it goes around the nail a bunch of times, it won't fall in the one nail case. So if we want to solve this problem for n equals 2, we need to find a way to do it such that if we remove one, it has equal numbers going clockwise and anti-clockwise around the remaining nail. Okay. Does anybody have any questions about this sort of train of logic? Okay, fantastic. So let's try and do it, right? Like we want to do it, and so we want, from the perspective of each nail to go clockwise and anti-clockwise the same number of times. So let's start going clockwise, anti-clockwise around this one, and then I'm going to sort of loop back almost to the painting, because then it's easier to sort of see what the loops do. So this is just a stylistic thing. And then we go anti-clockwise around that. But now we want to go the other way around this nail. So we go the other way. And now we've gone once anti-clockwise, so we want to go the other way around this one. Okay. Now, staring at this, it's not immediate what's happening, but let's imagine it's made of string and that it's not so loose. Then I can draw it like the string will go from there to there, and then it will go up, and then it will go through there, and then it will come back over there. Okay, so from our n equals 1 analysis, we sort of try the first thing which looks like it might work, and it actually works. So, alright, so let's look at this. I guess it's easier to see if you had string in front of you that this won't fall. But it won't. Like if you imagine that this is sort of pulling there, you have really moved it around. Not a mathematical argument, but this is a valid way to animate it. And what happens if you remove this nail? Well then, this loopy bit now can swing around there and fall. Great. What about the other nail? Okay, we remove that, then this loopy bit can sort of contract, and then you've got this bit which can come around and the painting falls. Fantastic. So this solves our puzzle in the n equals 2 case. And this is a nice sort of, this isn't so complicated that you couldn't think of it yourself. But, when we were sort of analyzing the n equals 1 case, it gives you more of a strategy for doing it. Okay, now what about the general n case? Okay, so at present we haven't, it's not clear how to generalize this. And in fact, to do it in general, you need a hell of a lot of turns. You need to go clockwise and anti-clockwise around things a lot. It gets very complicated. Even verifying visually is difficult. So you really need some theory. So let's try and do it for n equals 3. Actually first, does anybody have any questions about this example? Or how we got that? Because yes, if you remember nothing from this talk, except the statement of the puzzle and the solution of the puzzle, and you go away and think about it on your own, or tell other people and say, here's an interesting puzzle with loops and hanging paintings and stuff, I'll be very happy. So really, solution, puzzle, now we're going to get on to some things. Well, more things. So let's try and do the same thing for n equals 3. Okay? So what was our strategy? Our strategy was sort of go anti-clockwise and clockwise around each nail the same number of times. Okay. Does that work now? So let's say 3 nails. Okay. And then we go clockwise around this one, clockwise around this one, clockwise around this one, then we go back, anti-clockwise, anti-clockwise, anti-clockwise. And it's not, well, I don't know how good you guys are at visualizing. I'm not that good at visualizing things, but this one doesn't work. So yes, it holds the painting up, but if you remove this, you actually get to this situation. So this is not a solution. And our sort of looking at things one nail at a time isn't enough to answer this problem in general. Right? No. Does anybody have any questions?
So I was curious, so would this be a solution if you remove all but one nail?
If you remove all but one nail, then yes, this would be a valid solution to that. So that's sort of a weaker way you could approach this problem and say, okay, well maybe instead of removing any individual nail, what if we remove n minus 1 of them? Which is sort of another way of generalizing this original problem. There's lots of different ways one could do it, and you can sort of get insight by thinking about these different cases. And I think this is the case which is probably the hardest. But that's a much better sort of intermediate step. And yeah, you can check if this does work for that. So there's clearly something going on. Sort of in all of this, there is real sort of maths happening behind here. It's not completely obvious what it is, but it's sort of to do with the properties of little strings that are allowed to move through the plane and aren't allowed to move through these crosses. So for anybody who's currently doing Juji's course, some of this may be a little bit familiar. I don't remember. There was some assignment, and they were looking at the punctured complex plane with little loops that you're allowed to wiggle around. And so this is in the same vein as that. So yeah, so maybe I'll just state the maths behind it looks at loops in the R2 take away some finite set of points. So I won't harp on about this because you may not have seen this sort of stuff before, but this is basically maps from a loop to R squared minus P1 blah 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 Pn, where you mod out by wiggling your loop. Wiggling the loop. So you could imagine that these strings, we're allowed to sort of wiggle them. I mean, you can even see as I've been drawing them, I haven't really cared like where the string is. It's more where the string is up to just like wiggling it like a string. So I only really cared how it interacted with the names. Okay, and so this, I'll just say, falls under the category of algebraic topology. Okay, but I need not say anything about that. Alright, but maybe I'll say, I won't say anything about what this means, but topology is basically the study of spaces. And here we're clearly dealing with properties of spaces. We've got sort of, strings in a plane and we want to wiggle them around and such. But topology is sort of the study of spaces where you don't care about like angles or lengths. It's like a very sort of floppy thing you can do. It's like we see with these strings, we can wiggle them around and we don't care. We're not considering their like the lengths of the strings or anything like that. So that's sort of topology. Studies shapes up to a very sort of flexible notion of equivalence. And algebra is, things you can write with symbols. So algebraic topology is basically take spaces, which are difficult, and turn them into some algebraic objects which we can manipulate and understand in a more simple way. So, in other words, you think of algebraic topology as taking hard problems in topology and turning them into problems in algebra, which may or may not be equally hard, but which could potentially be more tractable. So, because I'm not assuming what we've all seen what a group is, I'm going to keep it pretty informal, and I'm going to use symbols to represent these loops. Okay? So, call this x1, x2. Oh, I'm writing x's, but let me say these are not the symbols that we'll be using to denote loops. I'm labeling my names. Okay, so slightly confusing notation. Sorry about that. And we're going to do our loops by saying, start somewhere, go around one of these x's, and come back to basically where you started. Okay, so, and we're going to remember the orientation. So this loop around this x1 is defined, I'm going to define a symbol for it, which is this. Okay? And I'm going to encode these like bigger loops, these bigger lists of things, in these symbols. Okay? So let's do some examples. So I'm going to think of this as like a function. I'm going to think of it as a function, but maybe I'll give an example instead of examples. So let's consider x2 composed with x1 composed with x3. Okay. And I'm reading things from the right to the left as if I'm composing functions. I'm going to use this to represent the following way of hanging something on three names. Okay, so first we go anti-clockwise around x2. And then basically come back to where we started. Then we go clockwise around x1. And then we go anti-clockwise around x3. And then we get back to where we started. Okay? So basically, this is to be thought of as a definition. We're defining these symbols to mean do this operation. So like you do a loop around one, do a loop around another, do a loop around another. Does anybody have any questions about this thus far? So, okay, let me say my own question about this then, which is like, why the hell can you do this? Like, this isn't particularly natural. There's a hell of a lot of loops. There are not that many symbols. Like, for instance, if I write them like this, it sort of looks as if you could, well, that they have a sort of associativity property, which is not obvious from the, well, it's not completely obvious from the topological picture. So, like, I know I'm sort of giving you the, saying, you can do this, but when you really get under the hood, like, we're doing something kind of weird. Like, we're representing loops or we're representing paths in this space as symbols, and there's some hidden theory which says this is sort of a faithful thing to do, like you're not losing information when you do this. So yeah, I want you to think of this passage as like, I don't know, it's not really, it's kind of deep, but you know, there's theory that goes behind the fact that you can even do this. But I will also say that we've already been thinking in this way, right? Like we've already been thinking going clockwise or anti-clockwise around separate nails, and so you know this does line up with our thinking, and so maybe it would be good for me to write this in terms of this way, which says, say, our loop goes that way, and first we're going this way around x2, and then we're going this way around x1, and then we're going this way around x2, and then we're going this way around x1. Right? Just so we have this sort of translation in our mind that we can sort of at least represent paths as these. Okay. So now I think I should probably say, well, I sort of alluded to this, but I'll put it as a theorem, because I don't want to talk about more. Theorem, this sort of loops / hangings up to wiggling this loop / hangings up to wiggling, these correspond to words, like words in this alphabet of symbols which are given by the nail, and then clockwise or anti-clockwise correspond to words in these things, say xi, such that xi doesn't occur. So, yeah, has anybody, yep, sorry.
I have one quick question.
Yep.
Are you, in your algebra, are you defining the starting and end points of your suspension?
Yeah, so
there's a convention right to left with the algebra, but the start and end is...
Yeah, so I'm sort of thinking of these as you read, this like encodes a sequence of things of tracing out a loop, and you read them from the right to the left.
But on the picture.
And on, oh, sorry, yeah, on the picture, it is, sorry, that's a really important point. In order to do this, we need to have a direction, because that tells us our start point and our end point. Yeah, that's really good. Yeah, because even here, it's like, when we want to say this, we need to say which way it starts if we want to talk about clockwise or anti-clockwise. Okay. So now, I want to maybe give some, or like a word in an alphabet is like a fancy term for, you know, just putting the symbols next to one another. Like there's really nothing more than that. And this is saying that, you know, you can put the symbols next together however you want, but you're not allowed to have clockwise and then anti-clockwise next to one another for any of the names. And this should be reasonably intuitive, because say in this example, if we went clockwise around here, and then we went anti-clockwise, well, it's like we did nothing at all. Okay, so like if we want to sort of capture the properties of the loops that we want, well, this is going to have to sort of be trivial, or not be visible in our words.
Did you want that to be one clockwise, one anti-clockwise?
Oh, I did, yes, sorry. Yep. That's a very good point. Yeah, so we want, oh, and also we want, yeah. So both of these don't occur. Very good point. Okay. So now I want to sort of describe the way to solve this problem in general, using this sort of algebraic gadget words in these letters. So the main point over this sort of formalism is removing a nail xi corresponds to deleting like this and this from the words. Okay, so maybe let's go look at this example, right? When we remove the nail corresponding to x1, and we remove these two things, we get anti-clockwise followed by clockwise. And this thing tells us that, or anti-clockwise and clockwise sort of, once you see them next to each other, they are the same thing as do nothing. So maybe a better way of saying this would be that these two things are the same as like do nothing, or the empty string, I guess. So from this we can like see that when we remove one nail, we get this thing, and then they cancel. We get nothing. Remove this thing, and this thing cancel. We get nothing. Fantastic. Okay. Does anybody have any questions? Yep.
Is it allowed to have two consecutive acts like clockwise?
Yes. Yes. So geometrically, so this would be 1, 2. Oh, this would be 3. Like 2 would be go around once, go around twice. It just hasn't popped up in the example. But yeah, that's completely valid. You're allowed to go around a nail lots of times. Yep.
So yes, so when we remove a nail, it somehow puts together two terms, which are one sort of clockwise and anti-clockwise on the same nail, which sort of, collapses it again, and then that happens until there's nothing left.
Yes, that's how we're going to solve the problem. Yeah. Yeah. So now, as that person pointed out, we can see that it's like, this now is more of an algebraic problem, right? Like we want to write a symbol in terms of clockwise and anti-clockwise, such that when we sort of set any of them to be trivial, that the rest of them sort of match up in pairs, possibly iterating down until the whole thing's true. And we want that to work for anyone we pick. And I mean, you can look at this and think, okay, this is now a precise algebraic problem. It's not clear that it's easier, but at least you can sort of look at it and it looks like a maths problem, right? Whereas, how do you solve this? Like we've sort of turned this very nebulous, hand-wavy thing into a precise statement about words in an alphabet. And that's sort of algebra, algebraic manipulation. Okay, so, all right, in the last 5 minutes, I'll give you the solution to the general problem. So this is, a problem in algebra. We want to work out a way to make things all cancel and make it work well. So the general solution, which may be familiar for those who have solved Rubik's Cubes before, is to use something called commutators. So given a word, which is some sequence of I, J, blah, 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 maybe it ends at, I don't know, N, we define its inverse to be going the other way. So going the other way, where we also reverse the orientations. So this one will be J, and then this one will be an R. Okay, so I'm now saying word to mean an arbitrary list of things built out of these letters, and I'm defining an operation on words which says reverse the word and switch the orientations. And then one can check that W inverse equals do nothing, or the empty string, but I'm going to define this to be a special element called E. Okay, so if you've got two words, you can put them next to each other, and that corresponds to just concatenating these lists. So if you have W and U are words, then we can say WU, say this one is this, and then this one is J, K. So if W equals this, U equals this, then this thing would be this, J. No, which way am I arrow's? Okay. Okay, so we can concatenate words. Concatenating our symbols